He's graciously decided to fill in for one of our speakers at the last second, so this should give all you confidence that you can fill in for somebody with less than 24-hour notice. You don't need 3 weeks to prepare. So we'll thank him for that, and we'll take easy questions in for that late assignment. And it's our pleasure to introduce Aaron Coenen, who started here in January 2012 as our senior research engineer. Probably you all know him. He got his bachelor's, master's from Milwaukee, University of Wisconsin-Milwaukee, and then his PhD at Madison, University of Wisconsin-Madison, and he was going to talk about work in his thesis, so we look forward to hearing about it. Aaron, let's welcome Aaron.
All right, thank you, Professor Raisler. I appreciate it. And yeah, don't take it too personally that you may be asked in the future to fill in last minute. I tried to scale this down a little bit. Hopefully it remains comprehensive for everybody, and hopefully it's still lengthy enough to provide you the appropriate information. This should give you an idea of what I spent the last several years working on. It's kind of a culmination of imaging, image processing and analysis, and overlapping that with mechanical performance of flexible pavements. So just a brief outline of today's presentation, the basics. We'll go through the introduction, some of the objectives that we were targeting to achieve with this study, overview of current practice since we have people in the room and possibly people viewing later that come from a background of granular materials, rigid pavements rather than flexible, multiple areas of study. So we'll try to get everybody up to speed on some of the flexible pavement current practices. I'll summarize the mechanical testing results, show you what ended up becoming a relatively systematic procedure for 2D imaging of HMA, and then get into some of the details of the study as far as the results. So in terms of an introduction, I was focused primarily on permanent deformation, or what you will commonly hear people refer to as rutting of the HMA. So whether it's caused by a combination of warmer weather and heavy loads, that tends to be an issue that we face with a viscoelastic material such as asphalt. So anytime you have your HMA that incorporates that viscoelastic material, you run the risk of rutting occurring. And I'll show you guys a picture that I had taken locally, and chances are you've seen this happen on streets in this area as well. So it is one of the common distresses of flexible pavement. The difficulty is it will occur even after the material is compacted to 92% GMM, which is the point at which it is allowed to be open to traffic. So even after it meets all inspection, all QC, QA criteria, we still end up seeing this distress occurring in the field. Density of hot mix asphalt, or HMA as I'll generally refer to it throughout the rest of the presentation, and mixed composition are currently used for that QC process. This does not account for the aggregate structure within the mix. So within the flexible pavement, you have the aggregate dispersed within the asphalt binder. Okay? So the current QC method does not account for the internal aggregate structure in any way. So this will become a means of trying to quantify that structure. So this was a picture that was actually taken in Madison, Wisconsin at an intersection just south of campus, the intersection of Monroe and Regent Street. Coincidentally has since been replaced, mainly because of utility work taking place in the area. But luckily, this very severe rutting has been corrected at that specific intersection. But again, many of you have probably seen that in this area as well, whether it's near campus where there's heavier bus traffic or because of our warmer summer climates in this area. You will see this occur. You may not even realize it until we have a heavy rainfall and water begins to accumulate in the wheel path, causing you to hydroplane. So it does become a safety issue as well. This will show you how critical the internal aggregate structure can be. These are two different HMA specimens with the same density and same proportions. Okay, so we do actually have the same percentage of aggregate, same asphalt binder content, and compacted to the same density or percent air voids. And just looking at a simple cross-section of the two, they look quite different. So the objectives for this study. First of all, develop a systematic imaging procedure and define measurable parameters to be able to characterize that internal aggregate structure. Later, verify the relationship of this internal aggregate structure to mechanical performance. If we quantify it, that's obviously only the first step, but it must be meaningful and applicable to real-world application. And then thirdly, demonstrate the potential for this to become incorporated into the criteria for mixed design. Okay, so it doesn't happen overnight, but really any work that is done should have an ultimate goal. And if this could progress to the point of being incorporated into mixed design, it would be most useful. So again, just to get people of various backgrounds up to speed on current practice within HMA, many of you are probably familiar with this, but most of the country, or all of the country now, since California was on board as of January, everybody in the flexible pavement industry is following the SuperPave mixed design method. So you guys have heard reference in your laboratories about GMM, GMB. So you've got your maximum specific gravity, you've got your bulk specific gravity, and we end up looking at the relative compaction of the material, or the percent GMM, which would be our GMB measurement. Okay? And this is going to become the acceptance criteria in the field, as current practice states. So we run laboratory, mix design, determine that GMM and GMB, and come up with our criteria for this 92% GMM. We've got a couple of illustrations here just showing how we currently measure that density in the field, or one of the methods that we use to measure that density in the field with the nuclear gauge. So we're able to determine the level of compaction for that field compacted asphalt. This is a table that hopefully looks somewhat familiar. This is actually straight out of Wisconsin DOT specifications, so it might be slightly different than what some of you are used to looking at, but it should be the same general breakdown, where we're actually classifying traffic. The areas that we want to focus on are the ESL classification, or the anticipated traffic loading. So you can see within that row, our table is accounting for pavements all the way from 300,000 ESLs up to greater than 30 million ESLs. This dictates our gyrations of interest. Okay, I'll talk a little bit more about this in the next few slides, but we actually predefined 3 specific gyrations during the laboratory compaction portion of mix design, and this will let us know what to expect from the mix in terms of behavior, at least slightly. But the area I really want to highlight is on the bottom of this table. So even ranging from anticipated traffic loading of 300,000 up to more than 30 million ESLs, look at the percent air voids in this table. We are still targeting the exact same percent air voids, or percent GMM, for this mixed design. So density is currently governing whatever we do with mixed design. Again, just to familiarize everybody, just showing you guys the typical gyratory mold on the right-hand side of the screen, and on the left, just an illustration showing us our angle of gyration. Okay. Our HMA is placed in there. We generally put a top plate on if it is not incorporated as part of the gyratory compactor, and compact our specimen to 160 gyrations during mixed design, so that we can look at that initial, the end design, and an end maximum, the 3 critical gyrations that I showed on the previous table. The way it'll end up working is you end up bringing your general aggregate source into the laboratory. We don't know what the required amount of asphalt binder is going to be. Again, we want to have enough asphalt binder to completely coat all of the aggregate that is in the mix, but not so much that it is freely flowing out of the aggregate structure once it is placed in the field. So in general, we try, during the mix design, several asphalt contents. We then look at the predefined end design, that critical number of gyrations from the specification table. In this case, 125. We are looking for the specific asphalt binder content that is going to give us that 4% air voids, or our 96% GMM, at that design number of gyrations, or 125 in this case. We then check the other 2 critical predefined gyrations, being N initial. We want to make sure that it's not too easily compacted, or it's generally referred to as a tender mix. And then N maximum. We want to make sure that this does not over-compact toward maximum. Okay, this is going to attempt to define the extent of the pavement service life, the 20-year design life. So we are targeting all the way from N initial up to N maximum, just to look at the behavior of this material during the compaction process. And then for those that are even more familiar with HMA, obviously we need to verify things like voids in the mineral aggregate, as well as the percentage of the voids that are actually filled with the asphalt. Again, we do not want to have our HMA structure flooded with extra asphalt binder that is extremely expensive and could potentially just run out of the aggregate. So what is the problem with this current mixed design method, now that we've summarized the method? Again, with everything being density-based, we can see that mixtures of similar density actually show very different performance in the field. Yet we are targeting the same density, regardless of mixture type. On the contrary, mixtures of different densities can exhibit very similar rutting resistance in the field. So where is the direct connection between density and performance in the field, specifically relevant to resistance to rutting, or that permanent deformation like we saw in the photograph? So some of the driving hypotheses that really push this work along, I'll just read them straight to you. Asphalt mixtures resistance to permanent deformation is more dependent on aggregate to aggregate contact rather than on volumetrics of the mix. Aggregate proximity index, which was defined throughout the course of this study, can quantify the connectivity of the aggregate matrix within the mix. A high level of connectivity is indicative of the aggregates forming a supportive matrix or skeleton, which provide better resistance to permanent deformation. So you can imagine, if you did not have a highly connected aggregate skeleton, as your traffic begins to load, it is going to slowly force the aggregate through that viscoelastic asphalt binder, if the aggregates are actually suspended within the asphalt binder. So the target is to increase the connectivity of that aggregate, and the binder is simply there to hold the aggregate in its place. But your resistance to this permanent deformation is going to come from your elastic aggregate that are directly in contact with one another in an ideal case. So the mechanical performance test that was used in this study to be able to correlate this with the imaging down the road was the flow number test. Some of you in here are familiar with flow number test, just defined here simply as a uniaxial repeated creep test, where we take a cylindrical sample of the HMA. We'll load it for a pulse of 0.1 seconds, a rest of 0.9. I'll show you an illustration in the next screen for the people that have not run the test or do not recall the specific definition of the test. But again, higher flow number typically corresponds to less permanent deformation in the field. Reason for that should become a little clearer here. So the top plot is our load. Okay? We are running in load control. So we can apply a specific stress to our HMA sample. And then we end up monitoring the strain response. So you can see from each loading pulse that we apply to the pavement, we do not actually end up with full recovery. So you can see the deformation that occurs, and then the recession of that deformation for the people in the room. During the unloading portion, we actually have a recoverable component. Okay? So there is an elastic component to all of it, but you can see there is not complete recovery. Okay? When we do not have complete recovery, we end up with permanent deformation, which is slowly going to accumulate one cycle at a time. So as we increase the number of cycles, we see this permanent deformation slowly accumulating. If our pavement is not recovering, we end up seeing this rut getting deeper and deeper to the point of being significant. So what we end up doing on a larger scale, if I go back to the previous slide, if we take the strain response here over several hundred cycles, in some cases a couple of thousand cycles, if we look at just that permanent deformation or that accumulated creep that happens one cycle at a time, we actually end up with a creep curve. Okay? The term creep is used by people in the HMA industry a little bit loosely. If people are coming from a strict mechanics background. Okay, that creep again is just that accumulated permanent deformation. If we look at it, in this case, over more than 1,000 cycles, we actually end up defining different zones along this creep curve, the primary, secondary, and tertiary zones. Okay, we have an initial response where we see a fairly rapid accumulation of that permanent deformation. And our secondary zone in the middle is where we have a relatively constant permanent strain per cycle. Okay, so we see a linear portion. Our flow number in this case, you can see labeled on the bottom of the plot, is at the current time considered to be the transition from that secondary to the tertiary zone. Okay, we can debate back and forth, I'm sure, for quite some time whether or not this is the most appropriate, but it gives us a relative ranking of the material as long as we remain consistent in our definition of something like flow number. Just to show you that it does actually occur, this is data that was collected in the early stages of this study. So the top plot is just showing you the total permanent strain versus the number of cycles. And the bottom is simply the derivative of that top creep curve. Okay, so what is the easiest way to define that transition from the secondary to the tertiary zone? Let's take the derivative and look for a localized minima, or the minimum point along that rate of change of that permanent strain, that permanent axial strain. And that is how flow number is defined in this case. What about this internal aggregate structure and the imaging component of all of this work? We ended up looking at aggregate proximity index. Several others have referred to this as aggregate contact points or aggregate to aggregate contact, which can be argued because, as I said at the very beginning of the presentation, we attempt to incorporate enough asphalt binder to completely coat all of the aggregate in the mix. So we end up with a thin film thickness of asphalt binder on all of our aggregate. If that is on each aggregate, how can two adjacent aggregate actually be in contact? You have that thin film thickness of asphalt binder separating them. So more appropriately, it is defined as aggregate proximity index. Okay? So we are determining the proximity of those two adjacent aggregate. The way we do that is there was not really an all-inclusive software available at the time that was capable of both the processing and the analysis of that processed image. So I had the pleasure of working with one of the professors from Michigan State at the time to try to develop a user-friendly and slightly more inclusive software that would take us through this processing and the analysis phase. So I'm just trying to break it down here. I'm not going to get into too many of the details of the software at this time. If anybody is interested, please come see me afterwards and we can certainly discuss this in greater detail. But what is happening in a very generic sense, you've got the processing phase of the software, which will take your captured image, whether captured from your iPhone, a digital camera, a flatbed scanner, or one of your planar images from a CT scan. You can take one of your cross sections. It will end up going through several filtering stages for processing to define specific regions of interest. Okay, those regions of interest in this case end up being numbered as aggregate, so we will define aggregate versus non-aggregate and take that to the right side of the screen or the analysis phase. The capabilities that we tried to incorporate into the software were the aggregate proximity index, which I'll focus on after this slide. We did not want to lose any of the research that was conducted previously, so we wanted to make sure we incorporated determination of aggregate orientation as well as segregation. So we can actually check the mixes to see if segregation occurred during compaction, whether field or laboratory. And then orientation, you can take it relative to horizontal on the screen, or you could actually do radial. So in this case, you actually see a circular cross-section on the screen. You could take something like a gyratory specimen and determine whether or not your aggregates are aligning in a radial pattern because of the compaction method. So this was used to actually compare multiple compaction methods around the globe. Again, we'll focus mainly on aggregate proximity index today and tie that into the mechanical performance. So just to increase user confidence, you do not have to be an imaging expert to be able to utilize something like this. Certainly advances can be made, but this was just trying to make it as easy as possible to address the hypotheses that were drawn up at the start of this study. So the software does have, within its user interface, the means of entering the known laboratory information. Okay? We know this if we're working with our materials, our aggregate and our asphalt binder in the lab. So we can enter our percent air voids because we're able to determine that. Our binder content we know, and the specific gravity of our two main components. Okay? Air being negligible in this case when it comes to specific gravity. So we enter this along with the known laboratory gradation. Okay? A simple text file just showing us the sieve size opening followed by the percent passing. So a very general gradation information. That gradation can be used in combination with the other specific gravity and so on that was entered to be able to, again, plot on the screen for the user the laboratory information or the volumetric fraction. So what percentage of the total volume of your specimen is occupied by your aggregate relative to the area fraction, or what percentage of the area of the image is occupied by aggregate, as well as gradation. So if you look at the two gradation plots, the red being your laboratory gradation, or being read directly from that text file, and the blue being an image-based gradation. So after the processing phase, what are we seeing for those individually numbered regions? Okay? What is the total area of those? What is the equivalent diameter of each of those identified regions? So we end up with an image-based gradation. If they don't agree, whether the gradation or the volume fraction versus area fraction do not agree at this stage, you need to adjust your filters that were used during the processing phase. Okay? So this is to allow people of multiple experience levels in imaging to actually process the image and come away with a little greater confidence that they have processed it appropriately before analyzing an image and wasting time on something that was not properly processed. Coming to the actual mixtures, as far as the testing, you will see that 2/3 of the mixes were used for flow number testing, the mechanical testing, and 1/3 of them went for imaging. Okay? This is just different mixes totaled at the top. They actually incorporated 4 different asphalt binders, okay, 1 neat or unmodified, and 3 different modifications, 1 with an elastomeric polymer, 1 with a plastomeric polymer, and 1 with GTR, ground tire rubber, or crumb rubber, as some people have come to know it. 2 different levels of asphalt binder content, or 2 different percentages of asphalt binder content, which directly corresponds to 2 different aggregate gradations, a coarse and a fine gradation. We know that a coarse versus a fine gradation directly affects the percentage of asphalt binder that is required to cover the surface of all aggregate. As well as 2 different aggregate types, both limestone and granite. And then the mechanical testing was conducted at 2 different stress levels, 345 and 1034 kPa, or 50 and 150 psi for people less familiar with the metric system. And that was selected to span the average stress experienced in the field. Okay, typical stress experienced in the field by the pavement has been found to be 89 to 90 psi, so 50 and 150 psi were chosen for this testing. The mixture testing was conducted at 46°C. Again, we're worried about this happening at higher temperatures. This may sound somewhat extreme to people because this is pavement temperature. It is not just environmental temperature. So this is 7-day average high temperature for the region in which I conducted this study, which was slightly north of here. So your temperatures may even go up a little. Looking at the gradations that were used, I said both a coarse and a fine gradation. They were actually pushed to the current control points. So this is the extremes that are allowed by SuperPave at the moment. Okay, so both the coarse and the fine at the control points, with the only exception being at the mineral filler level, the material minus 200 sieve, or smaller than 75 microns. Reason for that being there are several people that are extremely invested in looking into the influence of mastic, which is thought to be that mineral filler suspended in the binder and that is slowly, in some cases, being considered an additional component of the mix. So as to not allow the mastic or the amount of mineral filler to influence the results, the gradations were adjusted to have the same percentage of passing number 200. This should give you a better sense of what is taking place. On the left, you've got 2 gyratory specimens before any preparation is done. On the left-hand side of the right-hand side of the screen, you've got the 2 prepared specimens. Okay, the one cut and cored to go for mechanical testing, and the one on the far right of the screen sliced vertically, physically sliced to be able to capture 2D or planar images from that specimen. Where were they physically sliced? There has to be justification for nearly everything we do. So at the time, it made sense in my mind to divide this into 4 quadrants. The 4 quadrants being of equal volume based on the cut and cored specimen. Since ultimately the imaging results are going to be tied back to the mechanical performance, the cut and cored specimen for mechanical performance seen on the previous screen is what we're most interested in. So the CAD drawing on the left-hand side of the screen here is just showing the relative dimensions of that cut and cored specimen extracted from the entire gyratory specimen. And then the simple calculation that is used to determine 4 equal volume sections and the relative location of the physical slices. We have to treat the images similarly. So what I ended up referring to as digital coring of those images. Okay? There was no sense in actually cutting and coring the imaging specimens before vertically slicing them. So in this case, the entire gyratory specimen was cut, as seen in the previous photos. If you fan it open, again, look at the relative dimensions of the cut and cored or the mechanical testing specimen relative to the 150 millimeter gyratory. We can see we need to actually digitally core the image or crop it to match the cross section at each of those slices. Just showing that appropriate processing steps were accomplished. Okay? Very nice agreement between the image-based gradation and the known laboratory-based gradation, as well as volume fraction versus area fraction in this case. So this is just one screenshot of the study. You can use nearly any imaging software to capture a simple pixel intensity histogram. Okay, so after the processing phase, when this image becomes grayscale, so again, doesn't matter what device you use to capture it, you're converting this image to grayscale, and we're looking at the pixel intensity. This is a very common pixel intensity distribution for HMA. Proof is right here. Okay, 2 different plots, one for the coarse gradation, one for the fine gradation, and an image from each of the 3 locations. So just so it doesn't get too cluttered in doing 6 images, it's showing 3 in this case. So location A, B, and C as the physical slices were referred to. We see that same general shape of the pixel intensity distribution. What does that mean? We can define regions within that. Toward the low end, or the darker end of the grayscale, is considered air voids. Not all air voids are going to show up as purely black pixels because they're of varying depth and depending on the device used to capture it. So there is a range that is considered air voids. We see a small peak in the middle of this distribution, which comes from our smaller aggregate that have a tendency to be suspended in the asphalt binder. So it begins to contribute to that mastic phase that people are referring to. And then the larger spiking of this distribution toward the brighter end or the white end of this grayscale, the higher intensity, is the bulk of our aggregate. So in this case, our air voids or non-aggregate are being seen as darker pixels, and our aggregate are lighter pixels. So we can see this critical transition between aggregate versus non-aggregate is roughly the same for both the coarse and the fine gradation, shown by the dotted line on each of these plots. So coming in very near a pixel intensity of 150. So this is just to show you what is going to be done. One of the user-defined inputs of that software during the processing phase is a threshold value. So to eliminate all of the clutter of that pixel intensity distribution, we enter a single value known as the threshold value, at which point everything on one side is considered aggregate, everything on the other side is considered non-aggregate. And our grayscale image is now converted into purely black and white. So you can see we go from the captured image on the left to the black and white image after thresholding. So you can see some of the smaller, finer aggregate are lost during that thresholding. Some of those finer aggregate that were suspended in the binder. We can actually use the software then to zoom in on the remaining aggregate, okay, to determine what have we lost. Okay? We don't want to, if we have a 19 millimeter mix, we don't want to lose everything 12.5 and smaller. That's a serious problem. You've chosen the wrong threshold value. Okay? So here you're able to actually zoom in on the black and white image and determine the smallest remaining aggregate in that thresholded image. After that is done, for the fine gradation, for example, since we know we're working with smaller aggregate in this case, in the fine gradation rather than the coarse, if you do that thresholding for the fine graded mix, you end up with a smallest remaining aggregate of approximately 0.6 millimeters. Now, to treat all mixes in this study similarly, we need to take that 0.6 on the x-axis, come up and see where it intersects with the fine mix. Okay, about 22 to 25% passing. Okay, we want to take the same percentage so that we're accounting for the same quantity of aggregate in the coarse mix. And that actually gives us a minimum aggregate size to focus on of 2.36. Okay? Hopefully this makes sense to everybody. If you were accounting for everything 0.6 and larger in both coarse and fine, you would be accounting for a larger percentage of the aggregate in the coarse mix. Okay? Which we can see again by this plot. If you look at 0.6 on the x-axis, we have only 10% passing in the coarse gradation. So we would be accounting for 90% of our aggregate. But in the fine, again, we're just over 20% passing. So we're actually accounting for less than 80% of our total aggregate. So to treat them fairly, we are looking at an equivalent percent passing. Now, just an additional justification for aggregate proximity rather than aggregate contact. The two steel balls on the left-hand side of the screen are representing two aggregate. The yellow line on that image is representing our saw blade. Okay? If you take a specimen to the wet saw to physically slice it, if your saw blade is immediately adjacent to the true contact of those two aggregate in the three-dimensional world, you will see the top image on the right. Okay? The resultant planar view will show them in contact. As that physical slice moves away from that true contact point, you see in the planar image the distance between the two aggregate increasing. Okay? What are our chances of physically slicing that immediately adjacent to the true contact? Very slim. So we need to be able to account for that separation distance between aggregate. So again, I'll glance over this slide a little bit, but another user-defined input of that software that I had shown is the separation distance, or the surface distance threshold. Okay, so that is that distance between aggregate that you want to account for. You can assign that, and it should typically be assigned based on your image resolution as well as the filters that are being used during the processing phase. Jumping over that, once you define your surface distance threshold, or SDT, that will determine whether or not something is considered a contact point. Okay? So during the analysis phase of all of this, it will indicate, the software will identify the perimeter of each aggregate equal to or greater than the user-defined minimum aggregate size. Then it will look for the closest point between adjacent aggregate. If those two aggregate are closer than that user-defined surface distance threshold, it's considered what would have previously been a contact point, but is now a contribution to that aggregate proximity. If they're farther apart, it is not identified. I believe I've actually got a graphic of these results as well, so don't get too caught up on the specific numbers here. But this is just showing you what happens as that minimum aggregate size is changed. So again, accounting for various percentages of the total aggregate, coarse versus fine, and showing the 4 different binder types. Again, neat or the unmodified, an elastomer, a plastomer, and ground tire rubber. So this is just a graphic of that previous table. So again, it's just going to show you what happens to the relationship of the API, the aggregate proximity index, normalized to an area. Because again, you've got 3 different locations of slightly different cross sections as you approach the perimeter of a gyratory sample. So we normalize the aggregate proximity index. You can see what happens to the relationship. As we work our way from the left side of each plot, or the largest minimum aggregate size, in this case 4.75 millimeters, we don't see much distinction in the aggregate proximity index between mixtures of different binder types. As we start to account for a greater percentage of the total aggregate, accomplished by selecting a smaller minimum aggregate size, in this case all the way down to the 0.6, because that's everything that was not removed by thresholding, we can see that a distinction between 4 mixtures of both coarse and fine in terms of API begins to develop. So what? Are we just having fun with images, taking random pictures because I said you could use your iPhone to capture these? Is it meaningful? Does this correlate with the actual performance? Again, we don't have to get too caught up on the numbers, but just a summary table of the mechanical performance. The one I would like to point out in this case is the lower stress level of 345 kPa in this case, or roughly 50 psi. One of the modified mixtures ran for 50,000 cycles and did not fail. Okay? Failure, again, being defined as reaching that tertiary zone on that creep curve, where you can actually have the physical specimen collapse in front of your eyes. Okay? This ran for 50,000 cycles, no appreciable accumulated permanent deformation in that case, which is seen by this plot. Indicative of the low stress level of the study likely being too low to be meaningful. Okay, again, 50 and 150 were chosen to span the average stress experienced in the field, 50 likely being too low in this case, because we can see the mixture that did not fail. Only plotted to 10,000 cycles here, just so I don't terribly distort everything else on this plot. If we, however, look at the higher stress level, the 1034 kPa or 150 psi, and we look at that relative to the aggregate proximity index that was identified by the software, a relationship becomes quite clear. Okay? I apologize that this does not actually have the error bars on the individual data points. There was not time to re-enter that information, but know that it was extremely repeatable. The error bars are absolutely minimal, both in the vertical direction in terms of flow number between replicates and in the horizontal direction, or the aggregate proximity index between multiple specimens being cut and imaged. Okay, so even if the error bars were here, they do not overlap one another to drastically rearrange this relationship. So you can see, in this case, this is for the coarse gradation mix, and using that 2.36 millimeter aggregate. Okay, so accounting for roughly 75% of the total aggregate. We see a very clear relationship between the API and the mechanical performance. Same holds true when additional points, in this case being the red point that was just added to the plot. Mixtures of slightly different densities. Anybody that's worked with GTR or crumb rubber has noticed that compaction of it can be interesting. Okay, you can have swelling of those rubber particles, which has a tendency to actually rearrange your aggregate structure. How does that rearrangement of the internal aggregate structure ultimately affect the performance? We can see it does change it. And obviously, we drop to a slightly lower flow number when we compare the original GTR specimens to one of a slightly lower density or higher air voids. Okay? But it also reduced the API. So we are affecting the internal aggregate structure, but we're still able to quantify it, and it still fits the same relationship that was determined. Similarly for the fine graded mixtures here. Okay? Now again, using a minimum aggregate size of 0.6 to account for just over 75% of the total aggregate. We see the same relationship, slightly lower correlation here, now down to 95% rather than 98%. Still pretty nice from a statistical standpoint. Relationship still holds true when you introduce mixtures of different densities. In this case, another GTR specimen of lower density and a neat specimen of higher density. Okay? Not quite as convincing as the coarse graded mixtures, because we do actually see points falling off of a perfectly straight line. The reasons for this will be discussed in some of the recommendations for future work, but it also makes sense that, again, when we're dealing with a finer gradation, we run the risk of losing a little more of that information in the thresholding. Okay? It's heavily dependent upon your processing phase as well as your resolution of the image. So it tends to be easier in this case at the resolution of 1200 dpi used in this study to quantify the coarse aggregate. But in general, the software that was developed through some of this work serves as a means of establishing this relationship between flow number and API for a given mix. Okay? Doesn't matter if you had the same coarse gradation used here or the same fine gradation used here or even the same 4 binders. Okay? We see that a relationship has been established. There should be some range for this relationship, dependent upon the specifics of the material that you use. How can we begin to implement this? There have been previous studies, in this case, a Wisconsin Highway Research Program study. I believe this one was conducted by Ray Bonaquest, which several people in the room or viewing should certainly recognize the name. He had conducted a lot of work on flow number testing and ended up trying to suggest or recommend a minimum flow number based on your anticipated traffic load or your easels. We can start to make that shift toward a minimum API. So rather than saying we only want 92% GMM in the field or 8% air voids and we'll go ahead and open it to traffic, we can look at our specific gradation, at our specific binder, and determine an appropriate aggregate proximity index, which is indicative of the performance. Do we really care what the density is of the pavement that we're driving on? No. We're concerned with the performance of it. So if we have a means of estimating or approximating that performance, we are making an improvement. Okay? So rather than using a constant density for all HMA, this starts to allow us to slightly alter the required density. Even if density remains the easiest parameter to measure in the field, we can determine a more appropriate density for our specific pavement. So some of the conclusions from this study, again, planar or 2D imaging actually proved to be consistent, reliable, and repeatable when used to quantify this internal aggregate structure. That API is better in terms of estimating mechanical performance, specifically that of rutting resistance, than strictly density. Again, if you think back to some of the driving hypotheses and some of the problems established here, mixtures of different densities show similar performance. Mixtures of the same density, which we currently target, can show a wide variety of performance. So in this case, we are able to approximate the performance based on aggregate proximity. What was also noticed, because of some of the mixtures running to 50,000 plus cycles and not failing at the low stress level, is this third statement on the conclusions. At our higher stress levels that we ended up summarizing here, the aggregate structure dictates the performance of the HMA. But at the lower stress levels, the specific binder tended to play a greater role. Okay? So we don't know exactly where that transition occurs. Since we went from 50 psi to 150 psi, we don't yet know that critical transition from binder properties dictating performance to internal aggregate structure dictating performance. So just some of the recommendations here. Again, I don't think I need to read this directly to anybody that is viewing it, but the highlights that I wanted to point out, again, multiple densities. Let's start to increase the number of densities that are observed to see how we can begin to tailor the targeted density in terms of performance. increasing the resolution would make a big difference. Again, this study was conducted at 1200 dpi. If we double that resolution, we should be able to reduce our minimum aggregate size and account for a greater percentage of our total aggregate. And again, I conducted most of this work in Wisconsin, where we do not really use much SMA. You guys have a little more SMA in this region from my understanding, but given the gradation of an SMA, this may be fairly applicable in that case. And I have looked at a couple of images of SMA, and it was quite phenomenal in being able to process the image and quantify. I'd like to thank you all for your time, and hopefully we're on track to be able to allow you a few minutes for questions.
Thank you, Aaron. Any questions?
Okay, no questions. Thank you for your time. Oh.
Start with it. Thanks, Aaron. That was a good presentation. Quick question. When you are running the flow number, you are running it at high temperature. Now, the impact of the binder become very significant at this high temperature. And when you are looking now into the digitizing of the skeleton of the aggregate, you are more depending now on the aggregate structure. So I just would like to hear your comments, because if I change now the binder a little bit, my flow number will be different significantly.
Absolutely.
I know that you mentioned this is a mixed design specific, but does that mean every time I change the binder, I'm going to be doing the test again, even if I have the same skeleton of aggregate?
Right. If I can reiterate the question for everybody listening, it sounds like if you are only conducting your mechanical testing, flow number in this case, at one temperature, yet binders can be rated for multiple temperatures that will ultimately affect the performance, how are you accounting for this? Fair? What I didn't show you in this presentation is the details of the 3 modified binders that were used. The neat binder was a 64-22, if I remember correctly. The 3 modification types, the elastomeric polymer, the plastomeric polymer, and the ground tire rubber, were actually incorporated in a percentage to give the same PG grading for all 3 modified binders. Okay, so obviously increased from that of the neat. It did raise the high temperature grade, but they were consistent with one another. So the percentages of the modification incorporated changed. I think it was 2 grade bumps that I used from the 64-22, but all the modified binders in terms of conventional binder testing were graded the same on the high temperature scale.
Aaron, excellent presentation. Good work. I was coming from the imaging point of view, and and also I'm familiar with looking at asphalt samples on the 2D, and some work was done also by Bill Butler, Professor Butler here, his students, and usually what comes up in many of those cross sections, or the slices that we look at, is you're missing the 3rd dimension. And especially you mentioned in the contact points in a 3D, if you vary that line, you will have at one point contact, but you don't catch the contact at another point. I think proximity index here is really helping to with some certain assumptions capture those contacts, whether or not there's a likelihood of having a contact in the 3D structure. Is that correct?
Correct. What Professor is saying is, by entering that surface distance threshold, or that separation distance that we saw in the image, you are now saying if in this planar image 2 aggregate are within 0.1 millimeters of each other, for example, they are likely to have a 3-dimensional contact. If not there, maybe slightly in or out of that planar image.
Right.
So that is one means of accounting for that.
Indeed. And in 2D, it is really hard to judge that, but this is a good way to do this. When I was listening to your presentation, my immediate thinking was, as a ground truth validation of this approach, It would really help to mirror this maybe with some kind of some sample scan with the CT, X-rays, CT scans, and that aggregate structure, internal structure identified to check on those number of contact points. And also, if let's say if you did that, how instead of plotting flow number with the API, the contact points would give a correlation of what kind of R square and whether or not you have done that. So.
And initially, we did begin to investigate that because some of this work was being driven by involvement in RILEM, looking at different compaction methods. And what happened then is specimens produced by various compaction methods, both laboratory and field cores from LCPC test track, were sent to a centralized location. FHWA actually performed CT scans on these specimens. Some of those CT scans, or a three-dimensional scan, which is done every millimeter, for example, are compiled to recreate a three-dimensional structure. We did take some of those two-dimensional scans resulting from that, some of the single scans, and started to look at that when comparing different compaction methods. The difficulty is your significantly reduced resolution from CT scanning. So this allows a means of significantly increasing the resolution of a single image.
Right. Even though a few specimens analyzed like that, you could identify accurately the number of contact points and things, and maybe be able to relate to the API concept to better develop it, improve it even for future with higher resolution applications and things. So that's maybe something still in the future to pursue on this.
Yeah, there was I began to take a slight tangent to look for a representative element, for example, to see if there was a correlation not only between vertical and horizontal images, but if the resultant top and bottom surfaces of a cut and cored specimen for mechanical testing would be representative enough. Because then ultimately you begin to expedite some of this process. You don't have to prepare multiple specimens or separate for imaging. And then everybody's always saying, well, if you had 3 specimens of this mixture set aside for mechanical testing and an additional 3 for imaging, they were not the same specimen. So in an ideal world, we'd be able to scan that top and bottom surface of the mechanical testing specimen, which would be even better, or find a way to capture the perimeter of it.
Just a final comment. I mean, that would also help eventually validate some of the things for SMA type mixes, maybe more stone and stone contact, and as you move towards that direction, that those contact points identified from X-ray scans, CT scans could help, right?
Sure.
Yep.
And I'll elaborate on that a little bit while the microphone is being passed around. But we do have the difficulty here, the flow number testing that we're attempting to correlate the imaging results with is simply applying an axial force. So really, aggregate to aggregate contact, or the connectivity of that aggregate skeleton, is most critical in the vertical direction. But it becomes very difficult to distinguish between vertical and horizontal contact, or even vertical and horizontal proximity. So that is certainly a difficulty at this stage. We may begin looking at stress paths, for example, or the length of contact. So rather than a contact point or aggregate proximity, you start to actually account for the length over which 2 adjacent aggregate are within that distance of one another, because that's going to be representative of a contact surface in 3 dimensions. And okay, now how does that affect the distribution of stress as it's passed through the specimen?
Right. One other thing is you could also look at the anisotropy of aggregates orientation-wise in the sample. I know some work done by Professor Masad, Iyad Masad, and some follow-up research on that. In compacted basic samples, asphalt samples, how aggregates orientate in a way. Anisotropy in the vertical and horizontal directions the same way.
Right, and that's actually, if you think back to the analysis phase where I was just showing a very general overview of what this IPAS, image processing and analysis system, was capable of. I focused in this presentation mainly on aggregate proximity. One of the other options was orientation, and the reason we set it up so that you could define it as vertical or horizontal on the screen or radial is because it's going to be heavily dependent on your compaction method. Again, gyratory may influence it in a radial pattern, When you're taking a core from the field, you need to be able to identify longitudinal versus transverse direction, and in which case you would use strictly vertical and horizontal orientation on the screen.
You mentioned in the last slide that to increase the resolution, we can use a higher resolution camera. I'm interested in is the result will be affected by the illumination condition, especially for kind of contrast. So what kind of, did you use another light or did you use a natural light?
Very good question, because I did say you can use nearly any device you want to capture an image, okay? But there needs to be some sort of consistency. In this case, the 1200 DPI images were captured with a flatbed scanner in a completely enclosed and isolated environment. So the only light source was the built-in light source of that flatbed scanner. So it didn't matter if you captured an image at 6 a.m., 2 p.m., or 11 p.m.
So is the light white, kind of natural light, or do you know?
You're obviously going to interfere with it. I mean, if you were capturing this near a window, for example, you may actually begin to bleed out one of the corners of an image. Again, it's going to depend on the exact circumstances of where you're capturing this, but obviously control is ideal. If using a camera, again, in a completely isolated environment so you don't have external influence like sunlight or fluorescent lighting, just the flash of the camera for consistency in that case.
Yeah, I'm just thinking, is the white light proven to be the best case to increase the contrast, or because the white light contains all the wavelengths, maybe just use one wavelength, let's say blue light or red light would be better. I mean, is there any kind of publication to demonstrate like white light is the best one to do this kind of thing?
I cannot speak very intelligently on that matter. I didn't look into the influence of different wavelengths of the light source, but
because anyway you are transferring to the gray value to do all the things, right?
What was that?
I mean, you are transforming the image to the gray level. The
Correct.
gray level is the only parameter you are dealing with, right?
Correct. Correct. So it shouldn't matter. You should be able to test that. We did not, and I did not actually in a literature search come across anybody that did try multiple light sources of various wavelengths. But yes, you are converting a colored image, if capturing a colored image, to grayscale, and then later processing it to a black and white.
Okay, yeah.
I think we have enough questions, right? Do we have time?
Okay, well, let's thank Aaron again for his presentation.
Yeah. Once we're off the record, you can